In this lesson, we are going to be starting our waves unit. So this video is going to cover mechanical waves, and the next video will cover electromagnetic waves. So by the end of the lesson, you should be able to explain what a mechanical wave is, be able to identify different parts of a transverse wave, identify the different parts of a longitudinal wave, and you should be able to calculate frequency, period, and speed of a wave. So, what is a wave? Well, a wave is a disturbance that carries energy through matter in space. A lot of these waves we can't typically see, like sound waves, but there is an example of a wave that we can see. And those are the waves that you see like on Lake Superior or on an ocean. So, like I said at the beginning, there are two different types of waves that we're going to be talking about. The first one is mechanical waves, which we are going to cover in today's lesson. And then the other one is electromagnetic waves, which we are going to be covering in the next lesson. So, mechanical waves. These require a medium to travel through. So when I say medium, I mean some type of matter. So they either need a liquid, a gas, or a solid in order to travel. They vibrate either up and down or back and forth. So they either go something like this, or they go something like this. So some examples of mechanical waves are sound waves, ocean waves, ripples in water, earthquakes, waves of people at sporting events. All of these are things that you could be thinking about as we are going through this lesson. So now we're going to talk about the two different types of mechanical waves. So we have transverse waves and longitudinal waves. If you look at the picture here, transverse waves, they kind of make a line. It's like the waves that you typically think about when people are in the stands doing the wave, or the waves you see on the top of the water. Longitudinal waves are compression and refraction. So if you think of a slinky, when it's pushed together and pulled apart, or an accordion, it moves in and out like that instead of up and down. So a transverse wave. Transverse waves have particle motions that are perpendicular to the motion of the wave. So the wave is moving this way, but the particles are moving up and down. So an example of a transverse wave is a radio wave. So something that gives signal to your TV or your radio in the car. Those are radio waves, and they emit waves that look like this here. So there are multiple different parts to a transverse wave that we're going to talk about. So the first one is a crest, and this is the point on the wave with the maximum upward displacement. So the crest is going to be the very top of the wave here. So anything above this rest point, the peak above the rest point. A trough, this is the point of the wave with a maximum downward displacement. So this is going to be these pieces here below the rest point. So it's going to be the peak that goes below this rest point. Amplitude, this is the distance of displacement from the rest position. So here's my rest position. Here's my wave. The amplitude is the height of the wave from rest. So it goes from the rest point to the top of the trough or the top of the crest. So the greater the amplitude, which means the greater the energy. So the larger the height of the wave is, the more energy the wave is giving. So wavelength is the next thing that we're going to be talking about. And wavelength is the distance from one crest to the next, or one trough to the next. So wavelength is going to be from here to here, or here to here. They have shorter wavelengths. That means they have greater energy. So the faster the waves are coming, the more energy required to get them going as fast as they are. So looking at this picture, this kind of shows the things that we were talking about. Amplitude from the rest point to either the top of the crest or the bottom of the trough. And wavelength is either from crest to crest or trough to trough. So now let's talk about longitudinal waves. So longitudinal waves have medium that is moving back and forth in the same direction as the wave is moving. So the wave is going to be moving this direction, and the medium is also moving this direction. So if you're looking at this picture, it's what I was talking about with compression and refractions. So you've got the compressed wave here and the refracted wave there. An example of longitudinal waves would be sound waves. So just like with transverse waves, there are many different parts to a longitudinal wave. And we are going to be talking about each of them. So instead of having a crest and a trough, longitudinal waves have a compression and a refraction point. The compression point is the part of the wave where all the particles are crowded together. They're all really smushed. Refraction, this is the part of the wave where the particles are more spread apart, and you can kind of pick out all the other different particles that are in this location. So the wavelength is the distance from one compression to the next, or from one refraction to the next. So this picture just shows everything that I've talked about. The compression, remember that's where all the particles are kind of compressed together. You can't really tell the difference between the particles. So that's going to be this point here and here on this wave. Refraction, this is where the particles are more spread apart. They have some space to move around, and you can identify each of the pieces. So that's going to be these pieces here and here. And when we measure wavelength in a longitudinal wave, we can either go from compression to compression, so from here to here, or we can either go from refraction to refraction, from here to here. So the important thing to know when you are measuring wavelength, if you decide to do it from compression to compression, throughout the whole entire wave you have to measure from compression to compression. You can't do half of it from compression to compression and then do the other half from refraction, because this will give you an odd number and it doesn't calculate correctly. Now let's talk about surface waves. I didn't bring these up as a type of wave in mechanical waves because these are both transverse and longitudinal waves. And surface waves, so they have both a parallel and perpendicular motion. So they move with the wave and perpendicular to the wave, which is our water, which is the water waves we see in Lake Superior or in the ocean. So on the top of the water, you can see that the waves are moving in a transverse fashion. So they're going up and down. But if you think about when you have been swimming, you can kind of feel the water moving in more of a back and forth fashion. You can feel yourself kind of moving back and forth with the wave and up and down if it's pretty windy. So this is what we would then call the surface wave because it has aspects of both types of waves. So frequency is the number of wavelengths that go by in a given time interval. So And the equation that we use to calculate frequency is frequency equals waves divided by time. And the typical unit for frequency is hertz, or you'll also see it symbolized as an Hz. Another thing I wanted to talk about with frequency is this thing called resonance. It's the intensification and enriching of a musical tone by supplementary vibrations. So if you've ever heard people playing music on glassware, that would be an example of resonance. Or if you've ever seen videos where people tap a tuning fork and stick it on top of a glassware and it makes the noise of the tuning fork louder, that's resonance. So it's taking the frequency that it's hearing and it's vibrating and spitting it back out at that same frequency, but with a louder tone. So now we're going to do some examples of calculating frequency, and we need to use the equation frequency equals waves divided by time. So let's try the first one here. So a young girl is swinging on a swing that completes 20 cycles in 25 seconds. What's the frequency? So if we use this equation, our waves are the 20 cycles and our time is the 25 seconds. So we're going to set it up as 20 divided by 25. And if you plug this into your calculator, you should get a number of 0.8 hertz. So the frequency of this swing is 0.8 hertz. All right, let's try one more. So a clock clicks 88 times in 22 seconds. What's the frequency? Well, again, use that same equation, frequency equals waves divided by time. And our waves is going to be the 88 times. Our time is the 22 seconds. If you plug this into your calculator, you should get a number of 4, and your label should be hertz. So the frequency of this clock is 4 hertz. Now we are going to move on to talking about period. So a period is the time it takes for one wave to go by. So frequency was how many waves go by in a certain amount of time. Period is the other way around. It's going to be how long it takes one wave to go by. And in order to calculate this, we are given two equations that we can use. The first one is period equals time divided by waves, and the second one is period equals 1 over frequency. So depending upon what you're given in the question will help you determine which equation you need to use. And the unit that we use for period is seconds. So now let's do some practice calculating period. So a pendulum swings back and forth 8 times in 12 seconds. What's the period, and then what's the frequency? This is a multi-step problem where you are going to need to use both of the period equations you were given. So for the first one, we are going to need to use the period equals time divided by wavelength. So our time is Our time is 12 seconds, and our wave is 8. So if you plug that into your calculator, you should get a period of 1.5 seconds. All right, so now we've answered half of the problem. Now we need to figure out what the frequency is. So now we're going to use the P equals 1 over frequency. So to calculate the frequency, we are going to use the period from the previous equation. So we have 1.5 set over, we have 1.5 equals 1 over frequency. Now we have to rearrange this equation so that frequency is by itself. So you're going to multiply both sides by f, which will then give you frequency times 1.5 equals 1, and then divide both sides by 1.5. That'll get frequency by itself, and that'll give you 1 over 1.5. So then plugging this into your calculator, you should get a frequency of 0.67 hertz. So this was a problem that was great to do as an example because it showed the use of both equations. Now we are going to be talking about wave speed. So the speed of the wave is very dependent upon the medium that the wave is passing through. So it could be faster in gas than it is in a solid. Sound, on the other hand, is faster in a solid than it is in a liquid or a gas. The speed of sound is 340 meters per second, and it's 3 to 4 times faster than that in water, and 15 to 20 times faster than that in a solid. The speed of light is 300 million meters per second in empty space. And in our electromagnetic wave lesson, we will talk about what happens to that as it goes through water and gas and a solid. The equation we use to calculate wave speed is velocity equals frequency times wavelength. So this symbol here is the Greek symbol for lambda, and that is what we use to symbolize wavelength. So just below that, I have put the equation into words, just in case that symbol throws you completely off. So write it down either way that helps you. I would have it written down in both as a big recommendation, just in case on a test or something I ask you to identify what the Greek symbol is. The units we use for speed is meters per second, just like we've always done. So now let's do some practice with the equation I just gave you. So if a wave has a wavelength of 2 meters and a frequency of 500 hertz, what's its wave speed? So we're going to be using velocity equals frequency times wavelength, and our frequency is 500, our wavelength is 2, so if you plug this into your calculator, you should get 1,000 meters per second. Alright, so I have one more I would like to try. So if a wave travels at 10 meters per second, if the wavelength is 0.1 meters, what's the frequency and the period? So this is tying everything that we've learned in together. So the first equation we're going to have to use is this wave speed equation we just learned, because we have speed and we have wavelength. So our speed is 10, we don't know our frequency, and our wavelength is 0.1. Now we've got to get frequency by itself, so divide both sides by 0.1, and if you take 10 divided by 0.1, you should get a frequency of 100 hertz. So this solves half of the problem that we were asked to solve. Now we've got to find the period of this wave, and for this problem we are going to use the equation period equals 1 over frequency. So period equals 1 over our frequency from our previous calculation is 100. And if you plug those into your calculator, you should get a number of 0.01 seconds. So this example just shows that all of the equations we have just learned are intertwined. They can be used in many different formats. So the last thing I want to talk about today is the Doppler effect. The Doppler effect says that the motion between the source of a wave and the observer creates a change in the observed frequency. So it's basically saying, depending upon where you're standing, is depending upon how frequent you hear the wave or you feel the wave that the object is giving off. So if you look at the picture here, it's showing a train moving towards the guy in the front and moving away from the guy in the back. And what it's showing are more frequent as it's moving towards the guy in the front, but as it's moving away from the guy in the back, the waves are less frequent. So depending upon where you're standing, depends upon how frequently you feel or hear that wave. So now let's just do a little bit of recap of what we've learned, because I know that is a lot of information to take in on this lesson. So we learned that a wave is the disturbance that carries energy through matter or space. We've learned that there are two types of waves, a mechanical and electromagnetic wave. We learned that a mechanical wave requires a medium to flow through. And we've learned that there are two types of mechanical waves. You've got transverse and longitudinal. We know that transverse waves have a particle motion that is perpendicular to the wave. We know that the crest is the top of the wave and the trough is the bottom of the wave. We learned that a wavelength is measuring either from crest to crest in a transverse wave, or from compression to compression in a longitudinal wave. We know that a longitudinal wave has medium that moves back and forth in the same direction as the wave. We've learned that a compression in a longitudinal wave is where the particles of the wave are all compressed together. We learned that refraction is where the particles are more spread apart and have space to move around. And we learned how to calculate frequency using the equation F equals wavelength divided by time. We learned how to calculate period using two different equations, one being period equals time divided by wavelength, and the other being period equals 1 over frequency. And finally, we learned how to calculate wave speed using the equation speed equals frequency divided by wavelength. So, like I said, we have learned a lot in this lesson. So, please, if you have any questions at all, shoot me a text, shoot me an email. I will be more than happy to answer your questions or set up a time that we can meet so that I can help clarify any of this information for you. Otherwise, this is the end of our lesson, and have a great day.